And when you simplify a radical, the first thing you need to ensure is that your index is greater than the powers. And that's what we spent the whole time doing the last class. Okay, however, we kind of stuck with just square roots. This works for other radicals as well. So if I look at cube root of, let's say, cube root of 32x to the 7th y to the 9th. If you were looking to simplify this, you're looking for perfect powers of 3 or perfect cubes. Are there any perfect cube factors you can remove from 32? This is 8 times 4. 8 is a perfect cube. It's what is the cube root of 8? Comes out as a 2, and we're left with this factor of 4 inside our radical. How many groups of 3 can we remove from the x's, from 7? We can remove 2 groups of 3. When we remove 2 groups of 3 from 7, how many will be left? 2 groups of 3 is 6. When we subtract 6 from 7, we're left with just the 1. And how many groups of 3 can we remove from the y's? 3 groups of 3 gives you 9. When you remove that from the given 9, how many y's are left inside our radical? None. Okay, so here's our simplified form. Okay, when you look at that, do we need to consider absolute values? Was the index even? No, so you don't even need to worry about it. Just leave it as it is. Okay. The next rule that you need to consider, I mentioned, but we didn't really go through too much, and that is that the index and the power cannot share any common factors. Of course, other than 1. Okay, so here would be an example of that. Our first condition's met. Is the index greater than the power? Yeah, 6 is more than 3. And what's not met is the fact that looking at the power and the index, are there any common factors between those two? What goes into both 6 and 3? 3 goes into 3 how many times? Once. 3 goes into 6 how many times? Twice. So here we really get the square root of x. Okay. Are we done with that? Do we need to consider anything else? Was our original index even? 6, yes. So you do need to consider absolute values. So look and see. In our original form, could x be a negative number? The 6th root of x cubed. If x is negative and we cube it, we get a negative. Can you take the 6th root of a negative number? No. So x can't even be negative. Is that restriction shown in our simplified form? Yeah, you still see right here, x cannot be negative. So we don't need to put any absolute values here. It's already restricted from that, so you don't need to worry about it. And let me compare this to another form. And what if I did the 6th root of x squared? So it's almost identical problem, just a slight little difference. And when we simplify this, what goes into both 6 and 2? 2 goes into 2 once, 2 goes into 6 3 times. So we get the cube root of x. Okay, so the 6th root of x squared simplifies to the cube root of x. Okay, do we need to check for absolute values? Yeah, because the original index was even. And so let's test it and see. In this form, could x have been a negative number in my original form? If we took a negative and squared it, we get a positive. Could we then take the 6th root of that positive number? Yeah, so we know x can be a negative. So let's test and see what happens. If x is a negative, are we guaranteed that the cube root of x will be a non-negative value? And remember, any odd index, if it's a negative inside, which it can be for any odd index, then the simplified form will be negative 2. So the cube root of a negative number will be negative. So does that make sense the way it is? We know here that it's a sixth root, so it has to be positive. So we need to have absolute values around our x. Again, I do encourage you to be in the habit of checking for absolute values. And then the third and fourth rule we're going to talk about in the last section of this chapter, but these have to do with the fact that there's no radical in the denominator of a fraction, and there's no fraction inside a radical. These are basically saying the same thing, and if either of these conditions is met, we need to rationalize the denominator, which again most of you have probably done for square roots. That's the other point where students tend to miss a lot of the questions, is rationalizing when it's not a square root. But like I said, we will talk about this a little bit. Okay, what I would like you to do here is I'd like you to try sample problem. All right, so let's kind of talk through this. The first one, again, is a cube root, which we haven't done a whole lot of, but it's the same concept that we used up on the example above. And when you look to simplify that, you need to remove any perfect cube factors that you can. So numerically, what perfect cube factor can you remove from 16? So 16 is 8 times 2. The cube root of 8 comes out as a 2, and the factor of 2 is going to stay inside your radical. And you can move to the next base. How many groups of 3 can you remove from the x's? Just 1. And when you remove one group of 3 from 3, how many x's remain inside the radical? 0. Look at the y's. How many groups of 3 can you remove from the y's? One group of 3 can be removed from 5. When you remove one group of 3, how many y's will be left? 2. Do we need to consider absolute values in this? The index is an odd number, so don't even worry about it. This is the simplified form. Okay, the second example. Now, does everybody see the difference between this cube root 3 and this coefficient multiplier 3? And make sure that you can see that. If you're making mistakes on those, check with me, or if you have questions when you're taking a quiz in class, ask me if you have any questions whether something's a multiplier or an index. Okay, so this 3 is the multiplier, okay, and we're dealing with square roots. So are there any perfect square factors you can remove from 200? 200 is 100 times 2, so we have this 3 out front. The square root of 100 comes out as a 10, and this factor of 2 stays inside our radical. Moving to the x's, how many groups of 2 can we remove from the x's? Just the 1, with how many x's inside? 0. How many groups of 2 can we remove from the y's? 1, with how many left inside? And then finally with the z's, we have just the z left over. Okay, so when we simplify this, we have 10 times 3, which is 30, x, y, square root of 2, y, z. Okay, am I done? Or do I need to consider absolute values? Okay, our index is even, so I do have to consider absolute values, so let's test it and see. Okay, in our original form, can x be a negative? If x is negative, we're going to square it, and so it becomes a positive. So yeah, x can be a negative. Is that conditional, or does that affect either the y or the z's? No, it's by itself, completely by itself. So we need to examine that by itself. If x is a negative, does this form of our answer guarantee a non-negative value? No. So what do we need around the x? We need absolute values. Okay, let's move on to the y. So now we can disregard this. We've taken care of our x's. Can y be a negative? Yeah, y can be a negative. However, there's a special condition. If y is negative, then what do you know about z? Also would have to be negative. So let's test that case. Again, it's irrespective of whether the x is positive or negative, but if y is negative, then that means z would also have to be negative. So let's look inside our product here, inside the radical. negative times a negative, that'll take care of itself. But what about this y out front? If it's a negative, would that guarantee this whole simplified form would be a negative or non-positive value? No. So what we have to do is put absolute values around the y as well. So easiest thing to do, let's just extend this out. And we have absolute values around the product xy. This would be your final answer.